third and last talk for today and for this workshop, School on Cartan Geometries, and this is the talk of Jan Slovák.
Right, so thanks for being still all here. So it's amazing the whole week long. So mostly there was much more than 30 people here, even like in the afternoon. So this is the last talk of the meeting. And in the morning I was thinking about having too many pictures which I wouldn't be able to scribble on the board. So I decided to go through these slides, but they are as badly written as if I wrote on the board directly. So I will start with a few examples which you have seen during the week many times already, and focus on the part where I want to pay attention to, and that's, as I told several times, viewing the Cartan geometries as the basic setup given. That means you've got the Cartan connection, and the question is how to use the Cartan connection to develop some nice calculus. So in some sense, like if you are in Riemannian geometry, you know someone just gave you the Levi-Civita connection and the metric you don't think much about, and instead you know there is the calculus there. So the most common example here is the conformal four-dimensional geometry. We have seen that at least in the complexified picture or in the split signature picture, we know that it's given in such a way that the tangent bundle is identified with a tensor product of two-dimensional bundles together with identifying their top forms. And so it's like with all the Grassmannians we've been seeing here several times. And the structure of the Lie algebra, I mean, I don't know why, perhaps because we started this way very long back, I always have the positive ones up and the negative ones down, but I understand that if you writing code, and you have to go first through the negative one, so it's much more, I mean, it's also the projective parts are than here, and so I can imagine that writing the code would be better to start the vectors from 0 to n-1 and not the other way around, and that might be the different. But otherwise it's equivalent, as Boris told. And so this is the blockwise upper triangular matrix. So in this sense you see that the conformal geometry is actually in the line of examples which behave very similarly. There's the conformal, the CR, then the quaternionic conformal contact structures. And the only difference here is that because the matrices are antisymmetric, so in the corners here, I mean antisymmetric with respect to the other diagonal. So here in the corner we've got zeros, and therefore it's one graded instead of two graded, right? But otherwise algebraically it behaves very similarly. And if we go through the say technique, and knowing that we can dualize and we can look what the homomorphisms of the Verma modules are, then in the flat situation we get this kind of homomorphisms, and this is here for the de Rham sequence. So this is the 0 forms, exterior differential 1 forms, then the 2 forms split into the self-dual and anti-self-dual parts. So you have this diamond in the middle. Of course you can take the composition of those two arrows, and it happens with all the diamonds for all the parabolic geometries in these kind of pictures, that it always commutes up to sign. So if you go upstairs it's the same as downstairs, but with opposite sign, and therefore the composition of the d with itself will give 0 as expected, right? So this is actually 0, and here we have got again the exterior derivative, and then miraculously there is still one more operator, the long one, which is strange. So the symbol of the operator is the same as the square of Laplacian, and I will comment on that several times in this talk, because first of all we find out that if you start with any other say P equivariant, P invariant part of a G module, you take a G module and you look at the highest, so say irreducible G module, you look at the highest weight and look at what's generated by it with respect to the P action. And that's the first position here. So it's simply a P module with a weight which is G dominant. Right? And then it turns out that you always find the very same picture of differential operators, and the long one, and all of them, it happens that all of them will exist also in the curved versions, and the only exception is this long arrow, which mostly will not exist. And definitely it will never exist as a homomorphism of the Verma modules, as I was trying to indicate yesterday, that if we have an operator in the homogeneous world, then it definitely comes from a homomorphism of the Verma modules. If we go to the curve situation, we don't know that, but we know that if we find a homomorphism at the level of the semi-holomic Verma modules, then it will give us an operator. So the red ones are never obtained as homomorphisms of the semi-holomic Verma modules, but for the de Rham, the square of Laplacian exists, and it's called the Penates operator. And the reason why it exists is that we simply write down something which is not a p-module homomorphism on the level of the semi-holomic jets, but if restricted to the image of the universal operator I was talking about, then it is p equivalent. So actually, if we want something like one-to-one characterization of the invariant operators in a very algebraic way, then we have to talk about G0, so the reductive part of the parabolic algebra, homomorphisms which restrict to p homomorphisms when restricted to the algebraic subvariety in the jets defined by the Bianchi and Ricci identities. Right? And that's exactly the case. This has been computed explicitly. Right, what about other examples? So we saw already the Grassmannians 2 times n. So at the Dinky diagram notation, again, I talk about the split form first, so I don't color the dots here. So this is the Dinky diagram corresponding to the geometry. The P is having this algebraic structure with the slots of the sizes 2 and n. And here G is SLN plus 2R, P is this subalgebra, a parabolic one, and our manifold homogeneous space is G but P. If we go to the other real version, the quaternionic one, then we have to know that there will be the black knots here, and we have to have odd number of knots in the Dinkin diagram to have the real structure, so the real form there, and that will be the homogeneous model, which is the quaternionic projective space. And again, if we want to write down the de Rham, then we start with functions. Then the one forms are obtained again, so it's Grassmannian. So the characterization of the geometry is that the tangent space is identified with a tensor product of a 2-dimensional auxiliary space. That's the dashed ones, these indices, and the n-dimensional other space, and identifying the top degree forms. That's exactly the definition of the geometry, or at least one of the definitions. But if we go to the so the one forms are the dual to that. So simply the dashed index goes up and this one goes down. But if we go to two forms, we of course have to get something antisymmetric, so it's exactly taking the symmetric tensor product in the dashed indices and antisymmetric in the not dashed ones, or vice versa. And we can go on this way, and what we get is a system of operators. And you see that when I wanted to show this picture, I couldn't just scribble it on the board. Already the first one. And you see here that in some sense we see the parts. If I would go back, so here we had this theorem of this shape was this strange operator. And here we see it again, like here with this strange operator. Then it goes further, right? But in particular, you see that the previous picture is completely here. Why is this happening? Well, that's clear, because we saw yesterday that, 2 days back, that finding the operators in the homogeneous world is the same story as finding the singular vectors in the Verma modules. But what does it mean to find singular vectors in Verma modules? It means that you use some actions of the Weyl group, getting the raising and lowering operators in the structure of the Verma module. And if your Dynkin diagram sits inside a bigger Dynkin diagram, then of course you have at your disposal all these actions which you need, and therefore you know that the singular vectors must appear there as well. Right? So we simply know that the part of the picture will be repeated, and these operators are strange, and they really are strange in the new geometry as well as expected, and that was described nicely by Aleš Navrat, who also was sitting here for some while in the beginning of the week, is not now, and it was in his PhD under the guidance of Andreas, and for some strange reason it was never been properly published. So I will ask him whether he would come back and send it to our proceedings here, because it's nice results, and somehow it got not really completed for publication. Right. So that's the quaternionic example. Again, in the flat world, we get the very same picture whenever we start with something where the highest weight would be a G-dominant highest weight. So we know that the P modules are obtained so that we take weights which are P-dominant but not necessarily G-dominant. So usually you decorate the knots at the Dynkin diagram with some integer values, which says what's the tensor product, an irreducible component in the tensor product of the fundamental representations, except, and they always have to be non-negative, except over the crosses you can write anything, and that will give the action of the center then, right? So this is the picture. If we go further, and that's actually the motivation why I am talking about all these things here, because in spring this year we came back to the story with Vladimir Souček, and we decided to give it a try and look how far we can extend what we did with Mike Eastwood is, well, how many? Nearly 30 years back. And so what we wanted to discuss is this kind of geometry. So you have a odd number of dots, of knots in the Dynkin diagram, and put the cross in the middle. So it's like as Boris had this XOX geometry. So we have many O's, then X, and then the same number of O's to the other side. Why I think this is a very fascinating geometry? It's because this is yet another opportunity how to generalize in a natural way the four-dimensional conformal geometry which is in the background of gravity. You see? So the first try is to view the quaternionic geometries as an obvious extension, because this makes sense, right? So you still have the split of the two forms in reasonable way. You have one torsion and one curvature, and actually looking at this example explains why the self-dual Cartan geometry, so the self-dual geometries in four-dimensional gravity looks so much nicer, because in the quaternionic case you are left with one torsion and one curvature, and you simply want to kill the torsion. So the torsion-free one is in some sense very similar to the self-dual four-dimensional. Here, if you go in a similar way, you simply get again your tangent bundle as the tensor product, and unlike with the two Grassmannians, it's again two auxiliary bundles of the same dimension there, right? So therefore you can expect that it will behave somewhat similarly. Unfortunately, if you have more than one O here before telling the X, it's having only torsion, two torsions, right? So there are two torsions and that's it. But nevertheless, why not? And as I told earlier, it's not surprising that you see the picture from before again here, because of course, I mean, what I'm here depicting is this OOXOO case, right? So the first interesting one. And if you just forget one of these O's here at the beginning, you are sitting in the quaternionic case, I mean the two Grassmannian case. So the picture must be again there, and you see there, you see there is the wall, the right hand wall here in this 3D image, and there is the bottom there. So that's corresponding to removing one of the dots from the ends. And then there is a lot of other things, and fortunately, because everything is very algebraic, so in the flat world, this is the picture you always see. So it's simply what you have to expect to see. And this will happen for all the operators. And you also have these dotted ones, which is just the same story as those. But on top of that, you have some new ones, which are more intricate and not well understood. That's this one of order 7 in the theorem, and this one of order 9. And there is a strict similarity of another kind with the conformal geometry, because in the conformal geometry, if you choose correctly the coordinates, then you can write down the square of the Laplace. No, you can write the Laplace operator itself as a determinant of the first order derivatives, right? And this gives you the second order operator. Then the long one will be the square of that. And here you get a cube of the determinant. So that's the operator, that's the symbol of the operator. And of course, in the flat world, the whole operator is given by its symbol, because it tells you how to embed the highest vector of the Verma module from the target into the singular vector that's actually giving the symbol, right? And then the whole operator is then defined by that. It's from the algebraic picture quite obvious. So this is the end of my picture story, and our aim with Vladimir is to look at this particular example and try to understand whether you can obtain the operator also for the curved world, and how far, how much, just as an exercise to test what the theory, if someone does it, could look like. So let's go over now to the story, I mean the theoretical way. So a few reminders. So you see, I was claiming that Klein geometry just makes everything algebraic. I had this homogeneous space viewed as a principal bundle with the Maurer-Cartan form, and we saw that actually the jets can be identified easily with the derivatives with respect to the left invariant vector fields, and that gave us the identification of the, well, say, topological dual of the infinite jets with the induced module. And in our case, because I'm today exclusively only dealing with parabolic geometries, actually just a few examples only, so this means that we know nearly everything about the structure of the modules, about the structure of the homomorphisms, and so on. And I also managed to show the Frobenius reciprocity and explain that actually looking for homomorphisms is the same as searching for the singular vectors. And now there is a nice surprise. I was already sort of expecting everybody knows, because I was claiming that the pictures we get from the theorem will be replicating and getting the same with whatever module we start with, which is not completely true, but nearly completely true. And the tool to get there is the so-called Janssen-Zuckerman translation principle, or someone calls it the Zuckerman translation principle. I would have called it Zuckerman translation principle, but then I was told that he was American and no one would understand who he was. The simplified picture for this principle is as follows. If we take a G module instead of a P module, right? So we always can view every G module as a P module. No one can prevent us to do that. Then it's a nice thing to observe. It's just rather an observation, nothing complicated. Then in this case, what we do is we then take, well, I use unfortunately here, so I was using something I had before scribbled for some talk and changed quite a lot everything this morning, except I didn't change the notation completely. So what I was yesterday calling M for the induced module, it's now called V, right? Which is following the paper with Mike actually where we did it. So we have got a P module F and a G module W. And the observation is that the induced module for a tensor product of those two modules happens to be simply the induced module of the P module tensorized with this finite dimensional W, which is a very beautiful observation. Why? Because it means that if I get an operator, phi, say, it will correspond to a homomorphism between the Verma modules. So it goes from the induced module to F dash to the induced module to F. That's the dual thing to the operator from F to F dash, right? So I've got such an F, and I can simply multiply it, so it should be a tensor product here with the identity. I just take identity here. Then I take the explicit way how to understand this, and I get, on the right hand side, I get a new operator here. Right? And now I have to look at the included modules. And this is the core of the story, because there is one observation or strong theorem which I didn't mention explicitly yet, and that says that two Verma modules can enjoy having a homomorphism between them if and only if the center of the universal enveloping algebra has the same action on both. That's obvious, right? It's a homomorphism. The center is simply a center, so it commutes, and so it has to have the same action. And that's called the infinitesimal character of the modules. And these characters have been understood very well. You can see that two modules, so two induced modules, will have the same action of the center of the algebra if and only if they are on the same orbit under the affine action of the Weyl group. Right? The affine action of the Weyl group is easily computed. You simply take your Dynkin diagram decorated with the numbers showing how it sits in the tensor products of the fundamental representations. You add 1 to everything, that's the lowest weight. You employ the usual action of the Weyl group, and then you subtract 1 from the result. And what you get is a there and back translation, and a straightforward say exploration of what's happening shows that if you look at the module F tilde, which is sitting here inside, which corresponds to adding the highest weight of W, then it appears in this tensor product, this multiplicity 1, with respect to all others with the same central character. So there is no other one with infinitesimal character which would be the same. And therefore it splits off, and you can get out of this, and the same here, right? So you can get, by restriction of this, you can get nicely a new morphism of the Verma modules, and therefore a new differential operator. In fact, what's happening is that you have to embed your F tilde dash to this guy at the level of the modules, which means at the level of the operators you employ a differential operator. And the operator is of an order which is at most the length of the grading of W. That's another thing which I didn't explain yet properly, but whenever you take a G module W and restrict to a P action, then you get automatically a filtration there. And the filtration is easily computed by looking at the action of the center of the reductive part of the parabolic subgroup, right? And the length of the grading limits the order of the operator. And now if we want to, yes, so I will come to the claim one slide later. So now what we can observe that at the level, so we are still living in the homogeneous world, so at the level of the standard classical generalized Verma modules, right? And there we find out that not only if we take the highest weights of W or the lowest weights of W, the mechanism always works, but moreover, what we get is that actually what we get is two adjoint functors which provide equivalence of categories. And now I come to the crucial notion, and that's the so-called equi-singular cases, right? Because I was always claiming that when I had the pictures here, I was always claiming yes, and however we start, or better here, so whatever module we start with, if it's a G module, then it works. But what about, and all the other modules in the picture are obtained by the affine action of the Weyl group. But what about if we start with something which doesn't sit in the fundamental domain of the Weyl group as a weight, but sits on the boundary? Yeah, then in the affine action you will have many, well, it means that actually this one will not be P dominant, or not necessarily will be P dominant, and definitely there will be some weights appearing in the whole picture will not be P dominant. And at the same time, depending on how many walls it sits in the Weyl group, with respect to the Weyl group action, there will be repetition of the weights there. So you will have, for example, if I go back, so the Laplace operator is an example of having these kind of things. And what happens is you start with a weight here, which will be a P dominant weight, which will have something negative over the cross, but zero everywhere else. So it's a density. The right density for which the Laplace operator will be conformally invariant, right? And then what happens is it sits just on one wall, so the next slot will copied the same way. There will be identity here. And these two will not be there at all. And this dotted line or this line will be the same lines because it will be another identity of two weights. And the Laplace operator will be obtained as a homomorphism between Verma modules, but the Verma modules are not sitting in the scheme which is complete like here, but it's reduced. There are only some places here with some modules positioned there, and the others will be empty, right? And this is the so-called singular pattern. And the translation of this kind works very well if you take the highest and lowest weights, but always just goes to the pattern with the same singularity. So it will simply, for Laplace, you will get a lot of other things, right? And it gives you the two adjoint functions. And what we did observe with Mike was that actually, we may expect that the translation will work also for many other weights in the G module W, namely those where the condition will be fulfilled that in the tensor product you will find the corresponding components with multiplicity 1 with respect to the infinitesimal character, right? And therefore it will again split off. But yes?
I have to ask, W for you is a finite dimension?
Yes.
Okay. But then the highest weight must be in a positive chamber.
Yes.
Oh, okay. I thought you meant that they would be on the...
No. I mean, I'm talking about the affine action of the Weyl group. So it just shifts. Yes. So you start with something which is not in the chamber, but starting the affine action with the lowest weight added, you get to the wall. And that happens, for example, when you deal with the Laplacian. Right? So what we call, so this is just a extension of the translation, and the cost you pay is, well, actually twofold, right? Because first, you have to check that really the thing split off, and actually it sort of never works both ways. It always works only one way. So you do not have the adjoint, you do not have the adjoint going back, so there will be no equivalence. And the second cost you pay is that it's usually quite difficult to see that the composition going up, then tensorizing with identity and identifying in the tensor product your new components will give you something which is non-zero. So that you have to check this, right? Because that's not obvious, it will be non-zero. But it turned out that it was possible and was working pretty fine. And it was working in such a way that we were able to start with the most singular pattern, having just 4 identical weights in the middle in the diamond, and there's nothing else appearing there for all the dimensions in conformal. And then by this sort of skew one-way translation, we were able to construct Dirac operator, which we didn't have to because everybody knows that Dirac operator lives in the curved world as well, but it's possible. And then, because Dirac operator is on another type of equisingular pattern, right? And then out of Dirac operator, we were able to translate the Laplace. But the translation from Laplace to Laplace square simply fails. And on the contrary, we were able to prove that there is no homomorphism which would just go from the trivial representation of G to the top forms, right? And
how do you see Dirac? How does the Dirac operator appear in the pattern?
the Dirac operator is in the middle. So if you go to the Dirac operator, then the pattern is that this doesn't exist, and here are 2 equal things in the and two. Yeah. Right. So now the reminder is that I was claiming that we are building the semi-holonomic version to be able to go to the curved situation, right? And what we did with Mike and what we now want to extend with Vladimir and what wasn't successful enough, well, didn't work enough during summer to finish things is to understand how much of the existing homomorphisms, so how many of those singular vectors allow for getting the cover by singular vectors in the semi-holonomic case. And right, so just a reminder, so I was showing that we get this universal differential operator, and we can get again the Frobenius reciprocity, which we discussed the last time, and so the homomorphisms embedding the duals of the finite dimensional P modules into the semi-holonomic induced modules are the same thing as are not the same thing, but will provide us with operators, right? And we saw already, well, I discussed already that actually it does not provide all operators, because there are some exceptional ones which do not come from P modules. And of course what we can observe is that there is a filtration, like we've got the filtration on the standard Verma modules, so the same filtration will be on the semi-holonomic ones, and we can talk about order of the homomorphism by looking what's the level where the E star will be embedded to, right? So if we look here, so the E star has to, so the highest weight of E star has to sit somewhere, and the lowest K where it sits, so just the K where it sits, the lowest K which is hit by the image is called the order. And I don't have so much time as I thought to, so I claimed I will be scribbling here, so I thought I would show you explicitly, because it's very straightforward to see that if the order is 2, then there is always the singular vector cover, which corresponds to the fact which I told in the first day, that the symmetric classical second jets are sitting as a submodule in the semi-holonomic ones, right? And therefore all the second order operators, exactly as the first order operators, survive in the curved world without any troubles, right? So we didn't have to think about getting the Laplace from the Dirac, because we know that the Dirac and Laplace exist anyhow, right? So then, collecting all the messages together, you come to the situation that whenever you can get your homomorphism of the classical Verma modules by translation from something which exists in the curved world, so it means whose singular vector can be covered, then the translated one can be covered as well. And this was in the conformal world, depending on the fact that whatever W you take, it's composed by taking several such procedures with fundamental representations. And all the fundamental weights give you filtration of length at most 2. And therefore the splittings which you need to filter out the relevant components from the semi-holonomic Verma modules, they will exist all the time as well, right? Without any hesitation. So if you go into more general situation, you have, on top of everything I told already, you have also to check that actually your splitting operators you need to get the operators out of the picture do exist in the curved world. But there are many which do exist, because, for example, the construction of the BGG sequences uses the splitting operators as well, except it's only the exterior forms multiplied with some G modules, not all the representation. But for all of those, in all lengths, it always exists, right? So there is a good hope to find some arguments that it exists often enough. So, and just, well, I'm a bit behind the schedule, but I just have a picture to show. And that's it. So this is the picture you saw already. So that's the general non-singular case, right? So with the starting, I mean, perhaps you know that in our case, if we have the Dinkin diagram like this, so we would have something like A, B, C, D, E as the parameters telling which weight it is. And another way how to do it is you can write numbers like we have there. So for example, the 654 3 to 1 would be, without this, it would be a weight for the G. With this line, it would be a weight for the representation, and it's already the weight plus 1 everywhere, so edit with the added lowest weight. And it's very easy in this symbolism for the A to do all the operations with the weights, and so this is the notation there. And it has to be always, to be P dominant, it has to be decreasing here and decreasing here separately. To be G dominant, it has to be decreasing all the way, right? So therefore you see that the only G dominant one can be here, so that's the deram, right? The composition in our case. And when we go further, so this is the picture of all the operators in the flat word, where we have to discuss which ones will be there, and we tried a lot of experiments with the translations, and whenever we tried, they always worked except for the dotted ones, where they did not for the symbol ones, but we don't know about the determinant cube yet. And to see some singular ones, so for example, this is the double singular one where you would say that 5 is 4 and 3 is 2, and write the things down, and you have just one thing there, and they are always sitting in the general scheme as a part of it, right? So there are many of the types of the singular pattern. So this is another type of singular pattern. This is yet another 2 types of singular patterns, and so on. And these were all double singular. So the weight, so plus lowest weight would be sitting on 2 walls. And here is the one singular ones, right? And the one singular ones, they should, in some sense, topologically, the picture should be always the same as the 2 Grassmannian thing, right? So we have got, in this case, it's just nicely matched. If you choose another situation, so it's not seen at the first glance that it's the same picture, but it is, right? And here is an interesting one which just involves the 2 long operators. So we quite believe that the behavior will be very much, and the experiments show that we could be right, as in the conformal case, that simply you will be able to translate, starting with identity, you can translate one by one all the things except then all the singular ones, but the last step from the one singular to regular will simply fail for these very long ones. Right, so that's it, what I wanted to say.
Questions or comments?
So back to the Panites. So at some point you made the comment that it mostly doesn't exist in the third case. Can you sharpen that?
Yes. So for example, if you would stay with the densities, right, in the beginning and in the end, then of course you can take the Laplace, which does exist in the curve, and Laplace square, which does exist but not coming from a homomorphism. And then there is a theorem that the higher powers do not exist at all.
Okay.
Right? And the belief, at least I believe, that simply it's, if not unique, then extremely rare that it exists. So mostly it will not exist. the long arrows, and it's in all dimensions.
Can I just ask you about this?
Yes.
So I didn't get what this 65421. I mean, these are elements in the Hasse diagram, right?
Yeah. If
So
you subtract,
what is that?
if you subtract the two consecutive ones, then you get this plus 1. So this corresponds to 0, 0, 0, 0, 0. Because here I have the difference 1.
Okay. Okay.
And this is just another way how to encode it, special for the and it works very well because you just make the bar where your cross is, and it just allows you to work with the representation in a very efficient way.
Okay, thank you. Other questions? Comments?
Is there anything visible whether there might be a difference between torsion and curvature in the approach?
No, we haven't thought about. There is no curvature there. It's just torsion.
I know,
harmonic. Yeah.
but the question is whether this can be expected to make a difference or not.
Well, I would expect also in view of what Aleš was doing, that it will play a role, and it will play a role in the sense that I think it won't play a role in having the p-module homomorphisms there. It will be just the same, but the possibility that then some G0 homomorphism on the jet level would just be nice enough and equivariant with respect to the whole P on the image of the universal operator would be much more strange. So I would rather expect that it will simply not exist.
Other questions? If not, let's thank again.